In this video, we are going to talk about background jobs or background tasks. If you are a backend developer, understanding background jobs is very important so that you can build scalable and responsive applications or responsive backends. So, what exactly is a background task and why should you really care? So, a background task is basically any piece of code that runs outside of the request response lifecycle, right? This is our request, this is our response, and this is our client, this is our server, right? Any piece of code or any logic, any workflow which runs outside of this whole interaction, this whole client server interaction or the request response lifecycle, that we call as background job or a background task, which means that whatever that you are doing here outside of the request response lifecycle, this does not need to happen immediately. Right? This is not a mission critical task that needs to be responded immediately after calling it. Right? This is not synchronous. And that is the reason we can offload it to a separate process and finish however we have programmed it to finish. Right? However, we have programmed it to respond to whatever client or to whatever separate process. Why exactly do we need them? Right? So let's take an example. Let's say you have an user and you have a platform, some kind of SaaS platform. The user comes to your platform and they sign up. They sign up to your platform, which means they type their email, they type their name, they type their password, etc., and they make a request. And that request is made by your front end, whichever UI is represented to the user, and your front end makes a request or an API call to your server, to your backend, and your server does whatever processing, whatever validation, etc. it needs to do for the email, for the password, for the length of the password, for the complexity of the password, etc. And after that is successful, what it needs to do, it needs to send an email to that user, to this user, so that if you have ever signed up to different platforms, you must have noticed this workflow that whenever you sign up to that platform, you give them your email, you give them a password, and they send a verification email to your provided email so that they can verify that whatever email that you have provided, that actually belongs to you, and you're not providing any random email that you don't actually own. Right? That is one of the ways to verify that you own the email. What they do, they send a verification email which contains either a link which you can click on, and that redirects you to the front end and it asks you to provide a new password, etc., etc. Or it can also provide you a code, right? A 6-digit code or 8-digit code that you need to type into the front end interface, right? Some kind of one-time password. So this is how the workflow looks like when you sign up to a new platform. Now the point to focus here is user comes to your platform, they type their email, they type the name, the username, whatever, and they click on sign up, and your front end makes a request, an API call to your backend, and your backend does whatever the initial processing it needs to do, and then it sends an email to the user. Now, this is the task that we want to focus here, the sending the email to the user. And this is one of the examples of a workflow or a task that we usually offload to background processes. And the reason being, when you want to send an email to a user, what actually happens is you are subscribed or you are using some third party application, right? Some third party platform to send your email, some email provider, right? It can be a provider, some modern providers like Resend, Brevo. There are a lot of email providers that we use, and how it actually works is you construct whatever the content of your email is. Let's say you have an HTML template that you want to send to the user, and you fill the template with whatever code or whatever link that you want to send to actually verify the email. And you take that HTML template and you provide what is the email address that you want to send to, which is the email address of the user, and you provide the subject, you provide which email that you want to send from, etc, etc, right? Whatever the default parameters is for sending an email through an email provider, an SMTP provider. And you make an API call to a different service. Your backend makes another API call to the server of whatever email provider that you're using, Resend, Mailgun, etc, etc. Now that server processes your email, it checks whatever it needs to check, whether you own this email, whether you have the correct API key, etc, etc. And if everything is successful, it sends the email. However, that server has configured to send emails, and it sends the response back to your server that whether the email sending was successful or not, or whether it is a failure or not, etc, etc. Now, the reason we want to offload this to a background task, offloading this particular interaction, your backend calling another backend or another server for sending the email, is because this server may not be as responsive as our own server, right? Because we don't have control over other servers. And for some reason, for some kind of traffic spike or some kind of service downtime, etc, there can be a lot of reasons. So for some reason, let's say this service is down, and assuming we were not doing this whole email sending workflow in a background job, we were doing it synchronously. What happens? Your server does all the processing. It makes the database calls, it stores the initial data of the user in the database, and it creates a verification code, etc, etc, and it calls this API, and this API call fails. So there can be multiple paths here. One is if you are not properly handling the error of this API failing, and because of that, what happens? This API call, the user signing up, this API call, this also fails if you don't have proper error handling for this API, right? The email sending this API, and that gives a very bad user experience if your sign up API fails itself. Now, the second thing is, let's say you have proper error handling in place, and if you do have that, then only this interaction fails, right? The sign up API itself works properly, but this interaction fails. And even in that case, the sign up is successful, and in the front end, you are showing that we have sent you a verification email, and you can use that to verify your account, right? But since this never actually succeeded, and you told the user that we have already sent the email, so that again gives a very bad user experience. Now what they have to do, they have to come again to the platform, and they have to, if you have the functionality, they can click on resend email. And again, if the resend email, now that is a different API call. And by then, if the service is up, then all good. You can resend the email and they can verify the account. And if the service is still down, then again, this part of the API is failed, and you show the user that we have sent you an email again, right? And etc, etc. You can imagine how that experience goes. So that's how it works in a synchronous workflow. When you do all the processing in the same process that your API is working in the same request response lifecycle. Now imagining, let's say, let's go to a different diagram. We have a user, they come to your front-end platform, they type their name, type their email, and your front-end platform makes that request to your server, right? Now, the server does all the initial processing. Then what it does, at last, after doing all the processing, etc., generating the verification code, constructing the email, instead of sending the email or instead of calling the API of the email provider to send the email in the same method, in the same function, in the same request response lifecycle, what it does, it takes all the content all the information that we need to send the email, and it packages that into some format, let's say a JSON format. Like it serializes it into a JSON format, all the information that we need to send the email, and it injects it into some kind of queue, right? Some kind of queue. We have a lot of tasks here, or maybe the queue is empty at this point, it does not matter, but it pushes this task into a queue. And what it does, after it pushes the task into the queue, the API call does not happen at that point. It just says that this is a new task, this is a new function call that we need to trigger, or that we need to execute at some point, at somewhere. We don't know that yet, right? And it pushes that into the queue, and after that it returns. And by return we mean returns some kind of success status code, either 200 or 201, depending on whatever semantics that you're using. And because of this workflow, what happens, the user signs up and your front end makes the API call, and they immediately see that screen that we have sent a verification email to your provided email. So you can use the link in that email to verify your account. And that takes care of creating the task part. Coming to a different side of this execution, let's say here, after we created the task and pushed it into the queue. Now what happens on this side of the task queue is there are consumers, or depending on which framework or which language that you're using, there are consumers or there are workers, etc. What they do, they take out this particular task from this queue, and depending on the configuration, and there can be a lot of different types of configuration, and depending on what kind of scale that you're executing, if you have different types of nodes, different nodes for producers, different nodes for consumers. But we are talking in a very high level overview to understand how the workflow exactly works. What they do, they take out this task from the queue, some kind of consumer. And when I say consumer, what we mean is a program that runs in a different process from our main process, from our main backend application, right? This different process, it picks up this particular task, and since we had serialized all the information in the task into some kind of format, let's say JSON format here, it deserializes it into whatever the native language format is. Let's say if it's Python, it deserializes into a dictionary. If it's JavaScript, it deserializes into an object. If it's Go, it deserializes into a struct, right? You get the idea. It deserializes it, and it has now a native format for all the data that it needs to perform that kind of task. Now there can be different configs here. Let's say you have pushed the email into the email sending queue, right? There can be a different queue for sending notifications, for sending in-app notifications, or for sending push notifications to mobiles, right? Now different types of consumers pick up different tasks from different queues, right? Those all can be configurable depending on what library or what framework that you're using. Now, since it is an email sending queue, our email consumer or email worker picked up this task, and it was in JSON format. It deserialized into a native format, and now it has all the information that it needs to perform the task. Now what happens? It has all the information, and beforehand what we do in that consumer side, we configure from which queue we want to pick up the task from, and we also configure what kind of data that we are expecting to receive from this task, right? And that falls under the deserialization layer of the consumer. Then what happens, we also register a method or a handler, which is the code that actually runs when we provide it the data that it needs to use for running, right? Which is basically the same workflow or the same function that we are running synchronously when we did not have a background job, right? Which basically means here at this point, what we do, we take all the information that we need for sending the email, which is the HTML template, the sender email, the receiver email, the subject, etc., and the user ID, the user information for adding the user first name, for adding the user's email, etc., etc. Now it has all the data it needs to send the email. Now what it happens, it calls the API for sending the email from different email providers, depending on which email provider that you are using. It can be Resend, it can be Mailgun, it can be Brevo, right? Now this consumer, this finally calls the API which sends the user the email. Now usually what happens, all this processing, it happens between a few seconds or even milliseconds if there are not a lot of tasks in the queue. So latency is not a problem when you are trying to send an email, right? Because the expiry of, let's say, verification emails are usually 15 minutes or 20 minutes. And since our email will be delivered in milliseconds or max to max under 5 to 10 seconds, if you have a lot of traffic and you have a lot of tasks in your queue, right? What happens? This consumer calls this API and this service sends the email and the user receives the email and they can now verify their account. And in a different scenario, what happens, since we assumed in the previous example that if this service was down and our email sending this API call fails, right? This API call fails. What happens now is, since this API failed, this consumer process, this consumer function, that the handler that we registered with the consumer, this also fails, which means our task, this particular task has failed. At this point, if we were processing synchronously, the request response life cycle breaks and we return some kind of code. Since it's an server error, we return a 500 internal server error. Now that it's happening in the background, what happens? If a task fails, and depending on what framework that you're using, if you're using Python, you have something like Celery. If you're using Node.js, you have something like BullMQ. In Go, you have something like AsyncQ, right? Depending on what library or what framework that you're using for all this background task processing, background task execution, when a task fails, it is again injected into the queue for retrying. And for retries, we have different algorithms. One of the popular algorithm is exponential backoff, which basically means after a task fails, it will try after, let's say, 1 minute. It will retry that task. If it again fails, it will try after 2 minutes. It will increase the time. It will increase the hold time every time the task fails. And of course, we have a maximum amount of retries that we have configured beforehand, let's say 5 times. So after it fails the second time, we'll try after 4 minutes. After it fails the third time, we'll try after 8 minutes. And usually if you're using an email provider, a big email provider like Resend or Mailgun or Brevo, the services don't go down or your APIs don't fail for like 4 minutes, 8 minutes straight. Usually the downtime will be in seconds or milliseconds. So for those cases, it might fail, let's say once or max to max twice, but the third time it will most likely succeed. The service, the external service will be back up again and your email sending will be successful and the user will receive the email. And since we offloaded this whole email sending workflow to a background task, even if the external service was down, we were able to send the email successfully with all this retrying mechanism, etc. And that is another advantage of using background task processing, because of these very convenient functionalities like retrying mechanisms and failure detection, etc., etc. So now we have a very general idea about how background task processing works and why do we use them? What are the advantages? One of the advantage is the faster processing time, the responsiveness of our backend application, so that we don't block our actual API call because of some external service or because of some heavy processing. And second is we have retrying mechanisms for tasks which are prone to failing. Now, to summarize, background tasks allow you to offload time consuming and non critical operations. And because of that, your backend application, your actual backend API calls, they're responsive, they prevent timeouts because of dependency on external services, and it significantly improves your overall user experience. Now, what are some major examples, or what are some major kind of tasks that we usually in a typical SaaS applications offload to background? One which we already saw is sending emails. Sending emails, since it depends on an external service, we offload it to a background task, which we already discussed the whole workflow of. The second is processing images or videos. So if you have a workflow where the user uploads an image, and what you have to do is you have to take that image and you have to resize it, or you have to resize it into different formats so that the image can be optimized for delivery depending on the network conditions of the user or the device of the user. Since in mobiles, smartphones, we usually need smaller size images, and in desktop applications in big size 2XL, XL, etc., we need big images. For all these kinds of tasks, processing images or processing videos can be offloaded to background. Third, we have generating reports. So if you are running some kind of enterprise application, enterprise SaaS application, let's say take an example of a project management application. So you have to send weekly reports or daily reports or monthly reports depending on your configuration of the user. You have to send reports which are basically PDF files, emails of all the stats, all the process tasks, all the completed tasks, all the pending tasks, all the pending tasks in a sprint, etc., etc. In a typical project management application, you have to construct a email with all the content directly in the HTML format or in a PDF format. You have to generate that report in the PDF format, and you have to send the email daily at midnight at 12 o'clock, weekly on Sunday at 12 o'clock, etc. Right? For these kinds of tasks also, we offload them to backgrounds using cron jobs. Right? And if you're using a framework or a library like Celery, BullMQ, they also have features for scheduled tasks, so that you can configure a particular date, a particular time, and those tasks will be executed again and again on those particular intervals. Those features are provided by different libraries. Or again, sending push notifications. Push notification basically means all the notification that you receive in your smartphone, right, on your notification bar from different apps. If you have apps like Swiggy, Zomato, you receive these notifications to order food, or your delivery guy has reached a restaurant, etc., etc., right? These are called push notifications that your user receive in the smartphone directly on the notification panel instead of inside the app. And usually how it works is you have a backend. Let's say the Zomato or Swiggy, they have the backend. Whenever you install the app in your phone, let's say you install the Swiggy app in your phone, your device is registered under this push notification service. And usually it is provided by your operating system. So Google has their own push notification service, and Apple has their own push notification service, etc., etc. Now what happens, your backend has to store this device's some kind of code in their database, and whenever they want to send a particular notification to a particular device, they have to make a service call to Google or Apple, depending on which operating system their user is using. And these external services like Google and Apple, they actually send the notification to you. Not the backend cannot send the notification directly to your phone. It is done by your operating system, right? Operating system service. The backend actually stores the code of your device in the database, and it uses that to send you a notification. So since this workflow also involves making an API call, making a service call to a different service, external service, we also offload this to a background task. Now, these are some of the major examples of when do we actually use background tasks. in a typical backend application. Now let's get a little technical and understand what exactly is a task queue and how do they actually work. Now, to go by definition, a task queue is just a system for managing and distributing background jobs or tasks. And this is actually the mechanism, the behind the scenes technology that enables you to offload tasks, to reliably hand off the work that you want to do in the background to a separate process. That this is the core, let's say, engine that works behind the scenes to enable this whole workflow. Now, the core idea is you have a producer, which is your application code. It can be Node.js code or Python code or Golang code, right? Depending on what language you're using, what framework that you're using, your application code, which creates the task, and pushes that into the queue. This is the task queue. This is called the producer. The responsibility of the producer, the work of the producer is it will create the task, and that creation process will have all the information the consumer, the worker will need to process or execute the task. So the producer will take all that information and it will serialize it into a JSON format or any other kind of serializable format that your framework or your library uses. It serializes that data, it creates the task, and it pushes that into the queue. That is all the work of a producer. Then on the other side, you have the consumer. Which basically runs in a different process. It can be in the same backend application code, or it can be a separate code base also. Right? It runs in a different process, and what it does, it picks out those tasks and it actually runs them. It executes those tasks depending on what is the execution code or what is the handler that you have registered for a particular task. This is how the whole interaction works on a very high level. So this is like, imagine a to-do list for your backend. Your application code adds the tasks into the to-do list, and the workers or the consumers, they pick them off one by one and they execute them, right? A to-do list for your backend application. So technically speaking, on a high level, the producer, this part, it creates a task, and the task might contain information like the user ID or the user profile information like the name of the user, the email of the user that we'll need for processing that task. It will have all the information, and if it is an image processing task, it will have the image, or if it is a report sending task, it will have all the data that it needs to send the report, etc., right? And the producer, this process of pushing the task into the queue, it is called enqueuing, right? If you are familiar with data structures and algorithms, the process of pushing a new item into the queue, it is called enqueuing the task, which means adding a new item to the task. Now this part, this is called a broker. The queue is also called a broker. Now this is responsible for storing these tasks until a worker is ready to process them, which happens on this side, right? Other side. So this is like a temporary holding area until consumers or workers can pick up these tasks and start processing. And this part, the consumer or the worker, this runs in a separate process or a separate thread. The technicalities can be different depending on what language, what framework, and what library that you're using, but the core fundamentals remain the same. This consumer, it runs in a separate process, and the way it picks these tasks is it constantly monitors the queue for new items being pushed into the queue. And when it sees a new task, when it finds a new task, it dequeues it. The process of taking out an item from a queue, it's called dequeuing. And it dequeues that task and it starts executing it. So that is the high level technical overview of how a task queue actually works. Now, going a little more deep, when a task is enqueued, this is called enqueue and is called DQ. This is also called the broker, right? So when a task is enqueued, it is serializable. It is serialized into a JSON format, right? This is an important part of enqueuing a task. Now, this underlying system, this queue, so far we've been talking in a very abstract way, like task queue, etc. Usually, these are technologies. So, speaking of examples, this can be technologies like RabbitMQ or Redis, PubSub, right? Redis has a very useful module called publisher and subscriber module, which are usually used for implementing task queues, right? Or it can be SQS, which is a managed queuing service from AWS, right? If you are considering scaling your task management or task processing system to different nodes which are spread across the whole world, then Amazon SQS is a good solution, which is this managed service provided by AWS, which are deployed in multiple regions so that you have a very scalable and a very responsible task processing system in place. So this queue, this broker, which actually stores the task, right? This is usually managed by an underlying technology like RabbitMQ or Redis PubSub, etc. So what happens is when the worker or when the consumer, it completes the task, it sends an acknowledgement back to the queue. This tells the queue that the task was successfully processed and it can be removed. But if it does not send an acknowledgement, the queue can decide, depending on different parameters, that whether the task was unresponsive. In that case, it will try a different retrying mechanism. If the task failed, in that case, it will try a different retrying mechanism, right? All these frameworks like Celery, BullMQ, AsyncQ, all these very popular frameworks for task processing, they have all the features in place to manage all these different kinds of edge cases. In this whole interaction, we also have a concept called visibility timeout, which basically means that this is the period, this whole workflow, this visibility timeout is the period when a task is considered in progress, right? By a consumer or by a worker. And if the worker or the consumer, it does not acknowledge the task, it does not send the acknowledgement signal back to the queue within that timeout, right? Whatever timeout we have configured, depending on a configuration, if it does not, the worker, the consumer does not send an acknowledgement signal within the timeout, probably because it crashed or probably because the external service hung up. It can be a lot of reasons. What the queue will do is the queue will make the task, it will take the task and it will make it available to other consumers or other workers so that the task does not get lost in the whole interaction. And the reason being, since the way our task processing systems work is the publisher pushes a task into the queue and consumers take out tasks from the queue, they process it, and the queues remove the task from the queue, right? And since the consumer already took out a particular task from the queue and it was not able to acknowledge the success or the failure of the task, we don't want the task to get lost in the whole interaction. That's why we have this feature called visibility timeout. Because of that, the queue ensures that our tasks don't get lost, and when a consumer or when a worker is not able to send a particular acknowledgement signal, it will make that particular task available to other consumers or other workers so that they can start processing. So someone has to send an acknowledgement signal back to the queue to mark a particular task either as success or failure. Now let's talk about different kinds of tasks that we usually encounter in a backend application. So for the first example is pretty simple, that we have already seen one of task, which means something happens in your request response lifecycle, and you want to perform a single task, which is like a trigger. Depending on a particular scenario, we want to execute a particular function in background. So sending an email is a good example of one-off task. A user registered, you want to send them a verification email. The verification was successful, you want to send them a welcome email. And someone wants to reset their password, you want to send them an email so that using that link they can reset their password. Let's say it's a social media application and someone texted you and you want to send the user a notification. So that's again a one-off task, right? So these are examples of one-off tasks which you will encounter more frequently as compared to other tasks, but other tasks also have their place. Then we have recurring tasks. Recurring tasks are basically tasks which have to be executed periodically in specific intervals. And examples of that can be sending a particular report, sending daily reports, or sending monthly reports, or sending annual reports to your users for whatever the stats in that quarter, in that year, or in that month, or in that day, etc. Recurring tasks also can contain cleanup or maintenance jobs. So let's say you have an authentication system in place, and for authenticating users, you use stateful technologies. And for implementing stateful authentication, you have to store all the sessions of the user in your database in the sessions table. And what happens as the user logs in, logs out, logs in, logs out for a long time, they have a lot of abandoned or a lot of orphan sessions which are not really active, but they're still in your database since you never actually deleted them. So we have a task or a recurring task which executes, let's say, in every 3 months, or in every 2 months, or in every month, end of the month or starting of the month. What it does, it goes through all the orphan sessions, all the sessions which are not active and it's been a long time. So you actually go and delete them from your database so that you have some free storage. The orphan sessions are not taking unused space in your database. So those are some examples of recurring tasks. Then we also have chain tasks. Chain tasks basically have parent-child relationship between different kinds of tasks. So let's say you have an LMS platform. LMS means learning management system. So some of the popular LMS platforms are, let's say, Udemy, etc. Right? Now, let's imagine you have an LMS platform of your own, and what happens? The user, the instructor, whoever is creating courses in that platform, they can come into the platform and they can create a new course. And for creating a new course, what do they have to do? What they have to do is they have to upload videos. They have to upload videos into the platform, right? Now, a typical workflow of uploading videos into an LMS platform might look like: the user comes, they click on upload video, and they select the video that they want to upload, and they click enter, and the video starts uploading. And technically how it works is the front end takes that video and the backend immediately sends an acknowledgement so that the request is not blocked, but the uploading process is in progress, right? It can be uploaded to S3 using a pre-signed URL, right? The implementation can be different. After the video is uploaded, a number of tasks can be triggered. The first task can be the video has to be taken and it has to be processed so that the video is available in different resolutions depending on the network condition of the user or the device of the user, etc. Right? The video has to be encoded to different formats to cater to a wide range of network conditions and a wide range of devices. So that is your first task. And after that video is processed, and second task has to be triggered, which depends on the first task, which is the video has to be encoded first. Now the second task is the thumbnails for that video has to be generated, right? After the video is encoded to a particular format so that that video can be served efficiently from different CDNs or content delivery networks or whatever platforms that you're using. After the video is encoded, then we have to trigger a different task so that the thumbnails for that video has to be generated. After the thumbnail has been generated, now we have to trigger another task, which is those thumbnail images, they have to be processed so that we have different resolutions of the same thumbnail images for different network conditions and for different devices. Now this thumbnail image processing task depends on thumbnail generation task, but at the same time, after the video is encoded, at the same time we started the thumbnail generation task, we can parallelly start another task, which is transcription generation, right? The audio transcription generation to show to the user when the video is playing, basically the subtitles. Now this task, the audio transcription generation, and this task, the thumbnail generation, since they are not dependent on each other, they can be started parallelly, but they both depend on the task that the video has to be encoded first. So this kind of interaction, this kind of task chaining, this is what we mean when we say chain tasks, or tasks which have a parent-child relationship, right? Or some kind of hierarchy. A particular task can only be triggered once the parent task is triggered and successfully completed first, right? Those are examples of chain tasks. Then we have batch tasks. So one example of batch task from a real world example is, let's say you have a SaaS and you have a button where the user can click on delete account, right? A lot of SaaS platforms offer this feature where you can delete your account. Now, what happens when the user actually deletes their account? You don't actually, the front end cannot just make an API call, and the backend cannot just go through all the data of the user in the database, and they cannot just delete it in the same request, right? Since if it's a big platform, the user might have a lot of data, right? And they might have data in a database which are spread across different shards or different regions, etc., right? There can be a lot of different types of conditions and a lot of different types of data of a user that we have in the platform, and all of those cannot be deleted in a single request response lifecycle. Even if it can be deleted, it might take, let's say, more than 40 or 50 seconds, or let's say worst case more than a minute, right? And we cannot stall or we cannot block an API call for that long. And for that reason, what happens whenever the delete account API call is made, what we do, we immediately respond back with a successful response like 200, and we say that your account deletion task is in progress and the user is logged out from the platform, and they are given some kind of grace period that you have 3 days or you have 7 days to log back into the account and cancel the deletion process, or the account will be permanently deleted after the end of 3 days. That can be one use case. Or the second use case is, let's say you don't have a grace period, you're not a big platform like AWS. In that case, what we do, the moment the delete account API call is made, the front end immediately receives the successful response that the backend sends back, and it logs the user out. And for that user, the account is deleted permanently from our platform. But what exactly happens is, the backend takes, whenever the backend receives the delete account API call, what it does, it creates a task which is delete account, and it pushes that task into the queue, and it immediately responds back a successful response like 200. And the front end does its job. And for the backend, what happens, the consumer, which is responsible for actually performing the task of deleting an account, it picks that task from the queue and it starts the deletion process, which might be going through all the resources of the user. Let's say if it's a project management application, going through all the projects where the user is the owner. So removing all the entities of the user from that project, and then deleting the profile of the user, deleting the assets of the user like logos, cover images, and then at last actually deleting the user account, right? Then sending some kind of email to the user that your account has been deleted, etc., etc. So all of those things happen in background, which means our API call is not blocked. And that is an example of batch tasks, right? Because it involves calling a lot of tasks from a single task. So delete account task itself can call a lot of tasks for deleting the entities of the user, deleting the assets of the user, right? Those can be batch tasks, triggering a lot of tasks from a single task. Another example of a batch task can be, let's say at 12 o'clock, midnight, or at the end of the week, you have to send report to a particular user. Now, since you are a big platform, you have a lot of users. So at the same time, you trigger a lot of tasks, let's say thousands of tasks, which all do the same thing, generating a report and sending to the user. But since it happens for a lot of users, that also we can consider as a batch tasks, right? Sending thousands of reports to thousands of users at a particular interval. Those are some of the different types of background tasks that we usually deal with. Now, these are some of the design considerations that you have to account for when working with task queues or working with background tasks, especially when we are talking about scale, when you're talking about thousands of users, when it's a big platform, you're managing the back end of a big platform, and it's concerned about the background task process. First thing is idempotency. This basically means that whatever task that you're creating, that you're executing, you have to design them in a way that they can be safely executed multiple times without causing any side effects, right? In case of, let's say, failure of the task. Let's say, for example, in our delete account task, you have in our delete account task, in a typical delete account task, what you do is we go through all the resources, all the entities of the user in the database, and we start removing them, or we start setting them null, etc., depending on our requirements. Now, what we mean by idempotency in that context is you have to do all of them in a particular transaction, right? A particular transaction. So that what happens, let's say you start deleting stuff from the database, and down the road something fails, right? It can be something related to database, or it can be an external service call, right? Calling an API, getting some kind of data of the user, etc., right? It can be anything. At this point, if something fails here, if you are executing all of this in a single transaction, what you can do, you can do a custom rollback, right? A manual rollback. So what happens, since this task has failed, when the next time the task queue retries this task, we start from scratch, right? We start from 0% completion. And this is what we mean by idempotent. You have to design your tasks in a way that they don't cause any side effects in case something fails down the line, and you have to retry that task from scratch. Same way, error handling. You have to make sure that you have very robust and very extensive error handling in place, especially in task management systems, because everything is happening in a different process, right? So you have to make sure you don't miss anything. You don't miss any bottlenecks. You don't miss any edge cases, etc., right? So you have to implement robust error handling to catch and to log errors, also to retry failed tasks, right? So this is very important in a task management system. Then you have to set up proper monitoring. And what we mean by monitoring is you have to track the status of how many tasks that you currently have in your queue, what are the number of successful tasks, what are the number of failed tasks, and what is the major reason of failed tasks. Is it some kind of external service, or is it some kind of internal error, etc., right? At any point, you have to have the complete view of what is the status of your whole task management system. So you can use technology like Prometheus, right? Using Grafana and tools like that. So every time a new task is created, you can insert a new metrics. We'll cover things like metrics, instrumentation, elastic, ELK stack, etc., all these things related to logs, traces, monitoring in a different video. But we use this technique called metrics, where every time something happens, some kind of trigger, we create a new metrics and we insert it into some kind of stack. In this case, we have Grafana to monitor what are the different metrics currently that our backend application have, and we have ways to persist those metrics in disk, different replication techniques, etc., right? So for your task processing system, you have to have all these monitoring techniques in place so that at all times you can monitor what is the status of your system. Same way, you have to design your system in a way that it scales, so that down the lane, if you require more processing power, right? Let's say your user base spiked and you have to cater to more users now, double the amount of users now. So what you have to do is you have to add more number of consumers, right? So you have to design it in a way that down the lane you can scale your consumers horizontally, right? You can add more nodes to your consumers so that the processing remains as responsive as ever. Same way, if you require ordering, you have to make sure that whatever library, whatever framework, whatever task queue that you are using, they support ordered delivery, right? Tasks have to be executed in a particular order. You have to make sure that your particular library or framework supports that. Same way, we also have rate limiting. So if your tasks interact with external services, you have to implement proper rate limiting to prevent overloading those services, right? Because those services also charge you for number of API calls, and they also have their own API rate limiting technique, etc., right? So you have to take this also into consideration while designing your tasks. So these are some of the design considerations you have to keep in mind when you're working with a task management or background task management system. Now, talking about some of the best practices that I can recommend from my own experience of dealing with these background task management systems, is the first thing is keep your tasks small and focused, which basically means a single task should only be concerned about a single processing unit, right? You should not do a lot of things in a single task. So you have to design your task in a way that you have to divide the responsibilities between different tasks, so that if one task fails, it does not affect other tasks. If the one processing is dependent on a different task, then what you can do is you can go for chain tasks, right? You can have a parent-child relationship so that a task can be scaled in that way, so that even if the child fails, the parent does not fail, right? The child failing is a different task, so the retrying mechanism can handle that with exponential backoff or whatever. But if you do a lot of things in a single task, what happens is, even if the topmost processing is successful, but somewhere down the lane something fails, then the whole thing has to be repeated all over again, right? And if you are trying to add a lot of stuff into a single task, then that wastes a lot of processing power of your CPU, of your consumer, of your server, right? So if you keep your tasks focused and small, it's easier to scale, it's easier to avoid bugs, and it's easier to monitor them, right? And it's also easier for your queue to implement different mechanisms like retries, etc. Same way, always try to avoid long running tasks. If you have a task that takes a long time to complete, break it down to smaller and more manageable chunks, right? As I said, this is something similar to the above point. If you have a task which is doing a lot of stuff, then of course it's going to take a lot of time, which is a signal to you that it's about time that you divide this particular task into different tasks, either different tasks which are concurrently processed or different tasks which have a parent-child relationship depending on your requirements. Same way, using proper error handling and logging. This is, as I said, one of the most important things when we are dealing with background task processing. You have to have proper error handling in place so that you give a chance to your queue for retrying, and you have all the information you need to debug whatever happened in your task which made it fail, or whether it is an external service, whether it is an internal error, or everything. So you need all these error handling techniques or logging techniques so that it's easier for you to debug things. It's easier for you to monitor things, to find out where the problem is. And it's also easier for the queue to perform various retrying mechanisms. And at last, You have to constantly monitor queue length and worker health, which basically means you have to have proper alerting systems in place so that if the queue length exceeds a particular limit, you have to come up with different techniques to make it more scalable. Or if some of the workers are going down for some reason, you have to debug them, what exactly is the error that is causing them to go down, etc., etc. You have to have proper alerting mechanism so that at all times you are aware that your system, your whole task, background task management systems is running smoothly. Now, to recap, background tasks are essential for building scalable, for building reliable and responsive backend applications. And they allow you to offload time consuming and non critical operations to improve the user experience and to prevent timeouts and to enable retrying mechanisms for dependency on external services and for heavy processing tasks. That's pretty much all about task queues that you need to know as a backend engineer.